This is the survival analysis video on Kaplan-Meier survival curves in the absence of censoring. This video will describe how to create a survival curve in the simplest possible case, that is, where none of the patients in your data set are censored. As we proceed, I'll try to convince you that the survival and hazard functions provide equivalent information. I won't precisely define the hazard function beyond saying it represents the force of mortality. The stronger the force of mortality, the more quickly the patients in your data set will die off. If I presented you with the two hazard functions on the left, you'd almost certainly be able to correctly label the survival curves on the right. Your intuition might or might not tell you the two figures provide exactly equivalent information. In other words, that the survival curve is completely derivable from the hazard function and vice versa. To derive the survival curve more directly, consider a data set with 5 people and times of death as given on the slide. The survival curve plots time on the x-axis and survival on the y-axis. More precisely, what is plotted is the probability of surviving beyond time t. Since it's assumed that no one dies at exactly time 0, the survival curve always begins at 1. Since the first death occurs at t equals 10 months, exactly 4 out of 5 patients, or 80%, survive beyond 10 months. Thus, S of 10 is 0.80. Similarly, since the second death occurs at t equals 20 months, exactly 3 out of 5 patients, or 60%, survive beyond 20 months, and so forth. The proportion of patients surviving beyond time t is exactly the construct that you're looking for. However, the previous calculation will fall apart when censoring is present. This slide illustrates a slightly different way of making the calculation that will also work in the presence of censoring. The fundamental insight is that for a patient to survive beyond 10 months, 2 things must simultaneously occur. The patient must be alive at the start of 10 months and must not die during month 10. This insight sets up an iterative calculation, as illustrated in the table. The probability that the patient is alive at the start of month 10 is simply the value of the survival curve at the previous time point. The probability the patient dies during month 10 is simply the number of deaths divided during month 10 divided by the number of patients in the cohort at that month. In other words, this is the value of the hazard function. Similarly, the probability the patient survives month 10 is simply the number of survivors at that month divided by the number of patients in the cohort at that time. Equivalently, this is 1 minus the value of the hazard function. The iterative nature of the calculation, where we pull down S of t for the previous time interval, is illustrated in one interval via the red highlight. This illustrates the estimated hazard function for the previous example. Note that the number of patients at risk drops over time due to the deaths in the cohort. The Kaplan-Meier procedure generates not just an estimate of the survival function, but also of the hazard function as well. At this point, you should be comfortable thinking of most things in statistics as describing signal and noise. And here, the survival curve is the signal. Your intuition should also tell you not just to consider signals in isolation, but to somehow attach an estimate of precision to that signal. Turns out you can do this for survival curves, as illustrated on the slide. A common way is through something called Greenwood's formula, which we'll just treat as a black box that your software can generate for you. As you might expect, as the sample sizes drop over time, the noise associated with the survival curve will increase.